Okay, welcome everybody. We are now very happy to have a talk by Alain Goriely, and Professor Goriely from Oxford University is going to talk about the geometry and mechanics of chirality, from Maxwell's perversion to Feynman's obsession. Alain, to you.
Many thanks, Renzo, and thank you very much for the invitation to talk today. Since it's the end of the year and I'm sure everybody's a little tired, I thought that I would do more of a Christmas talk, so something more probably lighter than most of the talks that you usually have, and maybe with some more historical background. So I'd be interested in chirality, just to make sure that we are all on the same page, and you'll see why in a second. I just want to have start with some basic definition. If you have a curve here represented as a filament with a certain thickness, if you have no torsion of no curvature, it's just straight. If you just have curvature, positive curvature, you'll have a ring, and that ring is what we call a chiral. You can superimpose it on its mirror reflection. A left-handed structure would be represented by a left-handed helix and be defined with negative torsion, and a right-handed one would be with positive torsion. And if you want to make sure that which one is right or left, if you put your thumb in the middle and turn along the curve, you should follow the curve with your thumb. Or it's actually might be easier often if you take your right hand and you go along the side of the helix that is closest to you, it would follow naturally that part. But as Feynman says, that right-hand rule that we use in physics is merely a convention. It was a trick. And we'll talk about where this trick actually comes from and where the convention comes from. By itself, it's an interesting story in the history of sciences. We also need some equipped curve with curvatures. We've talked about curvature and torsion. These are just Freinet curvature and Freinet torsion. In general, for mechanical objects, we need a little bit more than that. So if we equip a curve, a sufficiently regular curve, say C2, with a right orthonormal basis, where the D3 vector is the tangent vector and D1 and D2 span the normal plane, then along the curve, if you take S to be the arc length, the derivative of this basis can be represented by a cross product between a vector U, the Darboux vector, and the basis itself. And so we have three components, U1, U2, U3, that forms the curvatures associated with this curve. It's not just the curve, you associate a curve plus an angle if you want. So it has more structure than a simple curve in space in this case. So the Freinet curvature and torsion, kappa and tau, are related to the elements of this Darboux vector, to this simple formula where we have introduced this angle phi, the angle phi that is often referred to as the twist or excess twist, depending on who. Curvature and torsion that are associated with the curve itself, and the twist, which is how the basis, or the basis that you define, rotate around the curvature. This has already poses problem, and there is a very good article by Feynman and Alexander about that, about this ambiguity, or you actually define twist and torsion, because as you can see, as the curvature goes to zero, twist and torsion become confused because they are the same quantity. So we have to be careful how to do that. There are plenty of nice mathematical ways to define it better with quaternion and things like that, but I'm not going to need this type of construction in my talk. Okay, so I'm interested in chirality. It's a bit, when you start thinking about this type of problem, it becomes quickly a bit of an obsession. It's something that I've been going back and forth for maybe 20 or 30 years when you first noticed the problem associated with it. You see it plenty in nature at different scale. You'll see it from buildings to trees or to twining vines or to umbilical cord. Umbilical cords have two arteries and one vein, mostly right-handed. And in seashell, typically, seashell have very well-defined chirality. Most of the current seashell, the one that exists now, are right-handed structure. These are all right-handed structure. You can keep going down, of course. You have structure, smaller structure. Arabidopsis, for instance, if you look at the root, you'll see that the root is mostly helical, and that helical structure is due to the fact that the root is actually made of files of cells that wrap around essentially a cylindrical structure. But you can go one step further. If you look at the structure of this cell, you realize that within the cell, inside the cell, you also have helical structure. It's also right-handed. You can go even further down if you look at protein like keratin. Keratin make you hair and nails and things like that. It's a double helix, as you see, and the double helix is made of itself of primary structure, alpha helices. And these alpha helices, as you can see here, is a right-handed structure. And that right-handed structure is itself inherited from the different amino acid. In this case, it's a left amino acid. The left or right definition of amino acid has nothing to do with the previous definition that I give you, all related to the right-hand rule and all that. That's only a convention of how you place different atoms in chemistry. So there are plenty of good questions related to chirality, and different fields have different type of problem and different name for it. I would say there are the hard question that in philosophy, what is the absolute or relative notion of space? Kant said, what can more resemble my hand or my ear and be more equal in all points than its image in the mirror? And yet I cannot put such a hand as is seen in the mirror in the place of its original. There is the problem of parity and symmetry breaking in physics. That goes back to the wonderful experiment of Ching-Chung Wu. Here is a description given by Feynman. This is the place in physics, the first level in physics in which there is a breaking between left and right. And before this experiment, this decisive experiment by Ching-Chung Wu, who unfortunately never got the Nobel Prize for which he should have had, the belief by all the experts, including Feynman, was that there was no symmetry breaking, that parity would be conserved in the decay at all level of physics. So that was really a huge change in our understanding of physics. And as Feynman says, the rule is that the particle which carry spin come out in weak decays with a spin mostly to the left. Now that is the rule, but today we do not really understand the whys and wherefores of it. Why is this the right rule? What is the fundamental reason for it? And how is it connected to anything else? And I don't think we know now. There is no more fundamental theory of physics that really addressed this one problem. Then there is the problem of chirality in both chemistry and in biology. What is the origin of chirality in nature? We see structure that are either left or right-handed. There are plenty of explanations that have been proposed, either from, for instance, from the infinitely small, like the weak decays, that says that creates the bias, or the infinitely large by some cosmic radiation. It's really not clear what says that. But it's a question that was really at the essence of actually all the work of Pasteur was trying to understand the question of chirality in nature. And that's how he made all these great discovery. And Curie, in the same way, that was a question that it will always come back about the origin of symmetry or the lack of symmetry. Of course, in biology, there is a distinction. For instance, if you look at the two hemispheres of our brain, they're not the same. The left and right hemisphere are not the same. And so there is a fundamental question, which is what is the function of that distinction between left and right, the function of what is called laterality. You see that all these fields have different names, but essentially for the same concept. Then there is the problem of selection of handedness in genetics. Why do population, something like 80 to 90% of the population is right-handed, and how is that conserved among the population? That's still not understood either. And then, of course, there is the left and right confusion in psychology, the fact that we're not very good at seeing the difference between a left-handed and a right-handed structure. Most people ignore that kind of distinction, all the way to people who print money. For instance, this bill from Argentina shows a left-handed DNA. Once you are aware of the fact that people do not pay attention to that, you see left-handed DNA just about everywhere when you read papers or anywhere else. These are the hard questions. You find this type of problem everywhere. But I'm not a philosopher. I'm not much of a theoretical physicist either. I have some small questions, what I call soft questions. I'm more interested in things that I can see, manipulate, and try to understand them at a more pedestrian level. So, for instance, you can ask the bathtub vortex problem. If you unplug, you sink. Will the swirl go left or right, and can we actually detect that? It goes back to very nice experiments that were done by Shapiro from MIT in the 60s, and then Trefethen did the same type of experiment when he was on sabbatical in 1965 for that kind of problem. Then there is the Feynman problem, the Feynman sprinkler. In his little book, Surely You're Joking about, Surely You Must Be Joking, Feynman described his experiment when he was also at MIT at the time, where he sees that a sprinkler system, if you just inject water, it would turn a certain way. He says, "What if I do the experiment, the reverse experiment? I put it in a big pool of water and try to invert it. Will it still turn the same way, or will it turn the other way?" It doesn't actually give the answer in his book, and it has led to a lot of interesting work since then. So this is a typical question in fluid mechanics where this inversion comes in. There are also very nice questions related to solid mechanics more. So one of the most fundamental objects of all solid mechanics is the spring. And of course, introduce the idea of the linear extension of the spring, introduced by Hooke in the 17th century. Here is a simple question. So the first question is, and I'll get to that in a second, as I told you. The second question is, if I have a chiral structure, how would it respond to loads? And that's very important because the chirality that you see in nature is not only due to the geometry, but also to the force acting on this object. So, very simple question. If I take a spring and put, for instance, some weight in that little basket here, so put a downward force, will the spring turn left or right? Very simple question. Will it wind or unwind based on the chirality? If I take this little double helix and I put a force on both sides, I just pull on it from both sides, will they unwind or wind? If I take a structure like the one I see in Arabidopsis in the plants, let's say if I take a fiber reinforced elastic cylinder and apply a force to it, will it turn left or right? These are not obvious questions. They're very elementary questions, but they're by no means obvious, as I will show you in a second. So I want to know chirality is not only created, but also transfer, because if you understand this problem of force acts on it and change, produce the torque in this system, then you can start answering the question of going from smaller scale to larger scale, because the chirality that you see at certain scale is not only due to the problem of the typical problem of chemistry is to look at these as a molecule as building block. And if you have a certain chirality and put the building block together and minimize the energy, that gives you an entire structure. But in this soft system where you have potentially deformation, then the force and the deformation itself can be chiral, as I'll show you. And so we can be in a situation where we can try to answer or chirality is transferred from one scale to the next and to the next until we see it. So these are the type of problem I'm interested in. But before I do that, of course, I want to find a good way to define and measure chirality. It's something also that's been occupying my mind the last few months. So again, very simple. I know that I've defined T's as left and right structure using the right-hand rule, and we'll see in a minute where it comes from. But if I know that, do I know if I give you a potato, for instance, if it's a left-handed or right-handed potato? You know, this is probably most likely any kind of potato you pick is a chiral structure. It cannot be superimposed on its mirror image. But how do we attach a chirality to a structure like that? Or structure that you like a trefoil nut. You know, we know that there are plenty of ways to define chirality in nuts, but if I just give a curves in space, how would I do that? And here I'm telling you right away, I'm not so much interested in the topological problem of chirality, but more in the geometric problem, and we'll see that it's not quite the same. So I want to go back to a little bit back in time, some history. Where does that left-right convention actually come from? You see that Karl Marx, a young Karl Marx, was himself very interested by the problem. Who shall determine which is the right and which the left? Probably if he had continued in his investigation on chirality, the world would have been different. But the person who actually brought the problem, who really was also quite obsessed with the problem, I call that Maxwell's other demon, was Maxwell. And in May, as he was building his theory of electromagnetism, he realized that in order for it to be well defined, he had to properly define operation like cross product and curl and so on, which he was the one to first define formally. And in May 1871, he wrote to his friend Tate, you know, there is no convention. I have a problem. I don't know what to do. And a few days later, he goes to the London Mathematical Society and brings the problem. And there is a nice write-up in a popular science journal called Nature on the proceeding of this meeting. And the conclusion, after a long discussion, the people like Kelvin are in attendance and other great mathematicians, and they discuss how should we define left from right. And he says, that's what's written, in pure mathematics, little inconveniences fell from the want of uniformity. But in astronomy, electromagnetism, and all physical science, it is of the greatest importance that one or the other system should be specified. Because we must have a convention. It's time to have a convention. And at the end of the proceeding, at the end of the discussion, they decide that, in consequence, the right-handed system symbolized by a corkscrew or the tendril of the vine was adopted by the society. So essentially, if you look at the first part of the sentence, it says, if you want to know what right-handed means, and so, or to define properly the cross product and so, all that, you go to your kitchen and find a corkscrew, and that's what defines handedness. So there is a comment about tendril of the vine, and that's also interesting. Based on that, Maxwell actually rewrite entirely the theory of electromagnetism with that convention before he had used the other one, the one that actually Tate also preferred, the other convention. But you find that in this treatise of electricity and magnetism, published a couple of years later, so very early in a footnote, you'll see that what Maxwell says. He says, Professor Miller has suggested to me that as the tendril of the vines are right-handed screws and tools of the hop left-handed, the two systems might be called tools of the vine and the hop respectively. The system of the vine, which we adopt, is that of linners and of screw makers in all civilized countries except Japan. So there is a lot to unpack in this footnote. Professor Miller was a professor of chemistry, and he was a very distinguished chemist, but he was no biologist. Otherwise, he would have known that the tendrils of the vine, the tendrils of the vine are actually not right-handed or left-handed, as I'll show you. The hop definitely is a twiner and is a very well-defined left-handedness. Then there is the problem of the screw maker. It's true that most screws are indeed right-handed, except there are some screws, for instance, you find in Eskimos that are left-handed. I have no idea, I really have no idea about the comments about Japan. I've been trying to find any reference about screws in Japan in the 19th century, and I haven't been able to find any reference that point to the fact that there might have been the other-handedness. So if any one of you do at some point, please let me know. That will resolve my problem. And he also talks about the convention of linears. So as you see, it's very much a history of confusion. Let's talk first about tendrils. He says tendrils of the vine. So when he refers to the vine, it typically means the genus of vines. And these are tendril bearers, the tendrils of the vine. And tendril bearers are neither left-handed nor right-handed. A tendril is a modified leaf that is typically left and right-handed. So that's for the first thing. The hop is a twiner and does not have tendrils. So that's another biological mistake from our friend Maxwell. But first, let's talk about the vine tendril. So it's neither left-handed nor right-handed. It's a problem that actually Darwin looked at in detail in his book on climbing plants, and that we look in the past with Michael Tabor, we look in the past to try to resolve. It's very interesting as such because it's a beautiful instability. Initially, the tendril attaches itself. It's perfectly, well, not perfectly, but straight. It doesn't have any very clear-handedness. And the growth induces an intrinsic curvature in the tendril. And because it's in tension and rotation is prohibited, you have an instability that takes place that creates this inversion. And I call this perversion, again, using that from a quote from Maxwell, which says that the operation for passing from one system to the other is called by listing perversion. Listing, as you may know, is a great German mathematician who introduced the word, who was the first to coin the word topology to describe the theory of shapes. The reflection of an object in a mirror image is a perverted image of the object. And indeed, Maxwell, when he talks about rewriting the theory of electromagnetism, says that he has perverted his entire theory, meaning he has changed from one convention into another one. So the vine system is not a good system to use. And indeed, this is the type of instability. If you start with a straight filament under tension and you increase in its intrinsic curvature, you find this left and right-handed structure, this beautiful structure that you can also find in telephone coil if you play with them. So let's go back even more in time with linears. So Maxwell said, I'll use the convention of linears, which is a good idea because, of course, Linnaeus is the one who made most of the convention in biology, who introduced most of the species name. And you can find that in Philosophia Botanica from 1751. And indeed, in page 39, Linnaeus, writing in Latin, introduced sinistrosum and dextrosum. And he gives example. You see this very nice little moon, either left on the left side or the right-hand side, to describe what is left and right. And he gives a number of examples of plant. Humulus lupulus is hop. That's the same one that Maxwell was talking about it. Convolvulus is a typical plant that is a very common twiner. And indeed, so here is humulus, and you see that if you follow, you'll see that it's indeed a left-handed structure twining around a pole. And here is convolvulus, and that's a right-handed structure. So no problem, very well defined. And you find that again in page 103 in the same book. You'll see again lupulus in the list, humulus and convolvulus. Same definition, no problem, very consistent. But here is the problem. In the third edition, he writes an erratum, and the erratum, he says, in page 103, when I wrote left-handed, you should really have read right-handed instead of sinistrum. You should read dextrum. But he doesn't say anything about page 39. If you look at the list, there is no erratum about page 39. So depending how you read the third edition of Philosophia Botanica, you would change your convention either from left or right. And indeed, the different authors in the 18th century and the 19th century, different plant physiologists have called this structure either left or right. So left people like Linnaeus, Gray, Eichler, Descartes, Darwin, all would call this left. But other writer would call the same structure right, like Linnaeus, depending on how you read it, de Candolle, von Moll, Biscoff, Sachs, all these great plant physiologists. And so again, there is a bunch of definition that you see in these old texts, that it's left view from outside, it's right view from inside, it follows the course of the sun. I never quite understand that. It's like the hand of the watch, all that to say that it's left-handed. Of course, the hand of the watch is also not very well defined, because you can look it from above or below. The same problem that if you place yourself inside or outside, what do you see rotate? So very poorly defined altogether. But we have a convention. Maxwell's convention essentially will just take the corkscrew convention. If a corkscrew is right-handed, and so we have a definition at least to start with. Now, the problem is the measure of chirality, what is left and what is right. So one of the problems that people have realized quite early on is that if you come up with a scalar measure, you get into a problem. The idea is to have a scalar measure of chirality that would give you +1, let's say, for right-handed structure, -1 for left-handed structure, and 0 when the structure is achiral. And we want, of course, this measure to be continuous. So here is a structure that is +1 right-handed at the top, -1 at the bottom, but I can sample any part of this structure to make a continuous family of these by just changing the point where I start. So the problem is I start at +1, I arrive at -1, so there is a point where as I slide somewhere here in between, which whatever measure I use, I will have, the measure would tell me 0, where the structure, since I've used different radii, the structure is by construction a chiral structure. And so this is the problem of chiral connectedness. There is no way to define a scalar measure that will always be that if it's 0 implies that the structure is actually achiral as this type of symmetry. And indeed, you do not expect to, with a single number, to have enough information for the entire curve. So a way around this is to go back to more a physical way to understand the problem and look not so much at the geometry of the curve, but the property of this curve in a given field. So the basic idea, you can think about a viscous flow, you can think about the wind acting, let's say, on this little trefoil. And what you want is you apply a uniform field, and you want to know if this structure would tumble or rotate in space. So that field would create a force F, that depends on the initial uniform field U. And in the simplest case, you can rewrite it as, if you have linearity, like in the Stokesian case, locally, you can rewrite it as a tensor F acting on U. And the tensor is given by the direct tensor product of the tangent with itself. And in the Stokesian case, it's C equals 1/2. In twisted nematics, you have the same problem of orienting field. You can take what is called cholesterics in the field of liquid crystal, and the C is also equals 1/2 when you define the helicity tensor that reorient the structure to create twisted nematics. But the force, you create more than a force. You can also create a torque. And if I look at this torque with respect to an arbitrary point R0, I have a force Q that's induced by the force F. It's simply R minus R0 cross F. That means the lever arm acting on the force, right? So at this point, at any point, I have a force F and I have a torque Q. Now, in general, these objects are a little complicated, but I can integrate all over the entire curve. I can do that. I can integrate these tensors, both F and Q. They have different names depending on the field, but I can integrate that over the entire curve based on a given point. Now, one can show, and that was first shown by Apple and Brenner in the 60s, that you can always choose R0 so that this Q, it's a chirality tensor, is symmetric. And you can further show by this property that it's a pseudo-tensor, that it's symmetric, it's traceless, and change sign in a mirror transformation. Okay, so now we have a tensorial object. We have a field, a tensor field that is defined for chirality. And you can define chirality as being given by the number of positive eigenvalues. That's a very nice construction. For instance, for this trefoil, it's really not that hard to compute. You can show that this geometric object will have two positive eigenvalues, and I can define that as being right-handed. For instance, you can do the same computation for family of torus knots, and you can measure chirality. With this nice parametrization, you can actually show that it always has the same structure with two eigenvalue lambda and one eigenvalue equals to -2 lambda for this particular parametrization. In this case, the center of reaction, the point where the chirality tensor is symmetric, is actually at the origin. Now, the curse of chiral connectedness is not lifted, however, because since the tensor is traceless, if you look at the second eigenvalue, the second eigenvalue will go at some point to 0 when you go from a right-handed structure to a left-handed structure, like I've done here, so to a left-handed structure and right-handed structure. The second eigenvalue would go to 0 at some point, and when it goes to 0, and since the chirality tensor is traceless, the lambda 1 and lambda 3 have opposite sign, and so I have no indication about chirality. So the curse of chiral connectedness is still there for this structure. I also wanted to tell you, as I told you, it's a geometric property. It's not a topological property. Here is a nice knot that I created. It has nice physical properties, but that's another story. But you can easily see that you can have as many turns inside of that. In this case, there would be right-handed turn. And that would eventually change the chirality without really changing the topology of the system. There is also another aspect, is that chirality tensor are interesting. And one of the property, of course, is that if I change u to -u, I would change the rotation. Another interesting feature is that since it's traceless, that means that it has three real eigenvectors. It's a symmetric matrix, but there is always a change of sign between the eigenvalues. So if an object, if I can find two axes where the object rotates in one direction, then there is a third axis where it rotates the other direction. So for this type of structure, you cannot find an object that would always rotate the same way under all possible orientation. Despite Kelvin tried to create such object. But it's also not enough. As I said, if you reverse u, you should reverse the rotation. But we know that there are objects that do not follow this rule. And one of the nice objects is the anemometer to measure the strength of wind. So if I apply wind to this structure, it will rotate a certain way. If I apply the opposite wind, it would also rotate the same way. Hence, this type of structure is not governed by a chirality tensor, so a tensor applied to u that would give me the rotation. There are higher order tensor that I would need to compute in order to understand the rotation of this type of structure. Okay, so we have an object, and recently I spent some time trying to find ways to define the same type of object for deformation rather than rigid curves. So let me tell you a little bit about the type of problem. So I told you we can look at a spring and you can ask the simple question, which way would a spring turn? And that's a problem I've looked in the past with John Maddox. And it was brought to attention by a series of experiments, very nice experiment on DNA. And what they did was that they attach a single strand of they attach a big bead on which they can apply a force and a rotation. And they can monitor the rotation of a smaller bead attached at a different place. So it's very much like a spring. You apply a force and maybe a rotation, but let's say you just apply a force and you want to know how this little bead turns. And they observe, and so the question is, will they turn left or right? And they publish in this Nature paper the big discovery that DNA overwinds when stretched. That means that as you pull on the DNA, it would wind on itself rather than open. And they thought that it was very bizarre because they said simple physical intuition predicts that DNA should unwind under tension. And then they showed that small distortion, contrary to intuition, DNA overwinds under tension. I said I was a little puzzled because, I mean, he's a great guy, Nick Cozzarelli and all that, and they have great intuition. I don't have great intuition, but what I lack in intuition, I can make up in computation. And so I thought, John, we really have to compute this, and we should start with a much simpler problem, which is if I take a spring, forget about intuition, and I load it, does it actually wind or unwind? And so we look at that problem in details, and we found that for actually all typical spring, so the one for which this ratio of torsional stiffness over bending stiffness is less than 1, all torsional spring will always wind first and then overwind. Overwind first and then unwind. And that's exactly what is seen in the experiment in the DNA. And so it's a completely generic properties that is all uniform, inextensible, unshearable, constitutively isotropic material, helical rod, will overwind first when pulled from the unstressed state and then unwind. So there will always be a point here where it would change its rotation. So as you just put more weight in that little basket, it would first wind on itself, and then at some point it will start unwind and go back and fully unwind. And if you look carefully, it's actually a property that you could have found in Tate and Thompson, who had nice so-called helical formula that tells you how a spring elongates and turns under a given force and torque. And indeed, we look at all the space of solution of equilibria of helical rods, and they all happen to lie on this nice quadric. And that under a moment m and force n, if you start at any point in curvature space, so this picture here is the 3 curvature that I told you about, U1, U2, U3. So that's the space in curvature. We show that all helical equilibria always lie on the surface. And as I apply either a moment of force, I go from one point on this surface to another one. And you can rewrite a local energy for this system that looks very much like a linear elastic energy, where zeta is the extension of the spring, theta is the rotation of the spring, and zeta is the coupling between the two. It tells you that as I pull, it also rotates. But the important point is that in large deformation, this stiffness coefficient evolve with the deformation. They're just a function of the deformation. So initially, it behaves like a Hookean, right? It's a constant for small deformation. But as you increase the structure, T is constant actually change with the deformation. So that also gives us, at the same time, I was looking at even looking at spring, what I could say about twistless spring. So if you take a simple spring and pull on it, you soon realize that it doesn't behave like what you expect from the Hooke's law. It's not linear for the reason I told you. This coefficient becomes coupled with the deformation. Essentially, they want to rotate, and without that rotation, they get locked. And if you do that on a spring, if you just pull vertically and prevent the rotation, the relation between force applied and displacement is initially like Hookean, it's linear, but soon it would go to an asymptote, it would get locked. However, if you take a left-handed spring and connect it to a right-handed spring, that's the right-handed is on the left side and the left-handed is on the right side in this picture. So if you connect the right-handed spring to the left-handed spring, the two rotation will much better twistless spring. It was such a great idea that a few years later, somebody in Harvard decided to make a patent out of it. But it's also a problem that gets more interesting because we found different ways to make a spring, and this is a construction that further uncouple extension and rotation, and that's what I call a much better spring. Now you can take initially these rings or rods that have intrinsic curvature, and you open them completely, make them straight. Both structures, they're initially flat, but you make them straight, and you connect them by little rigid rod. Essentially, you make a ladder. You assemble it, and this ladder, to minimize its energy, will want to actually twist on itself. And this twisted ladder, a very nice property. On the pure force, as you see, they just unravel, but in a very mostly linear regime. On the pure torque, they're very linear object, so they're very good spring. They're very close to an ideal spring, except for that coupling. But now you can play the same game and invert a left-handed ladder with a right-handed ladder with just an inversion here, a perversion here, and it has this beautiful property that under pure force, it extends without rotation. Just by opening that middle part, like it's the same type of problem you see in a molecule where you have a central part of the molecule that opens to balance the energy of the system. And on the pure torque, it doesn't increase in its extension. So in many ways, these two structures on the right are as close as you can be to an ideal spring, even in very large deformation. Now I want to come back to the problem of transfer of chirality. So there is a lot of problem in plants that not only requires change in curvature, but also change in torsion. It is a problem that was first brought by Darwin, actually. It's called circumnutation, where you plant a twiner looking for a pole, and once it's found a pole, starts climbing on it, hopefully soon enough. So these are time-lapse movies. It's on the scale of hours, of course. You always have to look at time-lapse to see what's going on in terms of motion of plant. And the same type of problem you find in octopus. I don't know why. I must have cut the part where it actually climbed. So what these different structures have in common is that they both create some form of torsion, and this torsion is managed by the content of fiber within the structure at a lower scale. So the general problem is that curvature is easy. It's some problem that's been solved by Timoshenko in the 1925. If you take a system of two metal bars with different heating coefficient and warm it, one is going to extend more than the other one, and since they are glued together, they're going to tend to curve. Here is a simple experiment of that, of this type of structure. And that's the basic idea that's in the many different devices, like the electric kettle that you see everywhere in the UK. But curvature is easy, but how do you create twist and torsion? If you go back to the equation, you'll see that there are two different ways to create torsion, or essentially two different ways. You can vary the twist angle to change the direction of curvature, which way the curvature goes, or you can actually vary this third component, U3, which is the sum of twist and curvature. And that's very different. So there are different systems that creates torsion. There are different ways you can create torsion. And torsion it's hard to create and it's hard to control. So we look at the general problem. I'm probably going to get a little shorter here because I wanted to bring you all the way to my favorite topic, which is the trunk of the elephant. The general problem is that I have a three-dimensional system. Let's say, take a big cylinder in which you have fibers, and these fibers can grow, or can, if they are muscles, they can contract. And I want to reduce that to a one-dimensional curve and see what is the inherited curvature and torsion. So if I tell you the activation tensor at each point, and I give you the elastic energy of the system, I want to know what is the curvature of my new system. So think about something happens in the stem or root of a plant. Some part grow faster than other, create curvature and maybe torsion. And I want to be able to describe that from the microstructure all the way to the macrostructure. And the idea is to do some form of homogenization and dimensional reduction. I'm going to skip on that so that I have a little bit more time to go to the system. But the idea is the following. If I embed fibers in my system and I allow these fibers to be active fibers, they can either grow or they can activate muscles. I want to know how the central axis of my system is going to change. So I give at each point of my three-dimensional domain, take a elastic tube, for instance, or a cylinder. I give at each point a direction alpha and beta, which give the orientation of a fiber. So it's a vector field defined at all points, a vector field defined on my cylinder. Out of that, I can show, these are, I think, the equivalent of the helical formula that I told you about Tate and Thomson. I call that curvature formula. If I give you the activation of these, the activation G of each of these fibers, so if I tell you how each of these fibers contract at each point, I can obtain the curvature, the intrinsic curvature of the resulting filament that I obtain in three-dimensional space. And it is a very generic and very general formula for that. So the takeaway message, I'm sorry I'm a little fast here. There was a lot of material that I skipped because that requires, it's a bit of a long story. But the important part for just this talk is that if I have a microscopic activation field G, so again, how each fiber represented, so a vector field, each one is activated, either a little longer or a little shorter, I can obtain the overall shape of this tubular structure, my new intrinsic curvature of my structure. And we applied that to different applications within natural science. One is the tropism of plants. So plant, for instance, some plants respond to the activity of light. They want to rearrange with light. I'm not going to go into the detail, but the idea that is there is a chemical that's being sent down the different part of the stem and induce an elongation of part of the stem that induce both curvature and torsion. Is driven by auxin with respect to the source tip and intensity. And here is a nice little simulation for this effect. That yellow ball is supposed to be the sun, and you see the plant following it, and at night it reorients itself. And that's again control of curvature and torsion by local intrinsic change at the level of the microstructure of the system. Here is an example of both circumnutation, as I showed you before, and twining. So that's the twining around a plane. You see here we started with Maxwell vine, and here is the equivalent where I have a law that dictates the way the fibers elongate, and that create torsion, and eventually that results in twining of plants. So my last topic, which we've been working very recently about is elephant trunks, which I always found fascinating. So if you look at an elephant trunks and you remove the skin, for instance, you'll find that it has a lot of very long longitudinal fiber. I thought actually it has more muscle fibers than just about anything, about 40,000 muscle fascicles. And if you remove that, you'll see more structure underneath. And indeed, if you take a cross-section of the whole thing, you'll find that the elephant trunk has both fibers that are longitudinal and fibers that are radial and fibers that are helical. So it has that different type of arrangement of fiber within the structure. One way to model that, and that's the first thing we try, is to have different segments that can be activated differently. But we didn't find that very convenient or very easy to realize experimentally. It's easy to do conceptually. And so we try to think about other possible design. How do we control both torsion and curvature? And one of the idea that we came up with is that if you think about a single ring, and the red part can be contracted. These are helical fibers that winds around the tube, and they can either contract or elongate by muscle activation or by any type of other activation. And you do that uniformly so that you attach one number, the extension, for each fiber. And so you have a system with very few controls, and the question is, what are the shapes that can be generated to this control? What is the map that sends activation numbers, let's say if I have 3 activators, to the geometric shape in space? And you can actually show that you can compute all this very elegantly, and then you can assign tasks for it. Here is an example where I have 3 fibers and I have 3 numbers. Gamma 1, gamma 2, gamma 3, that tells me how each of these are extended. And my task is to reach this target endpoint. And by just playing with these 3 numbers, so finding a path in this 3-dimensional space of activation, I can almost get to the target, but not very well. However, if I take 2 of these tubes, and the first one has 4 and the other one has 3, I can easily reach not only target, but I can also find a path in space that avoid obstacles. And so here's an interesting problem, and as you've realized, is a problem of robotics. I have a space of activators, and I want to know what is the map that sends these activators to a given shape in space. And in this case, with this construction, because we know how curvature and torsion are affected by this activation, we can actually write this map explicitly. Here is the actual realization. That was version 1.0 of our elephant trunk. And what you see as little fibers here, liquid crystal elastomer, when heated, they extend or contract, and they create exactly the type of activation that you have in this structure. But we were not quite happy with that because the experimental realization didn't work very well. They tended to split and all that. So we come up with another design, again inspired by the elephant. If you look at the elephant, it has a huge longitudinal muscle at the top, and that's what keeps That's what keeps the elephant trunk. That's what allows the elephant trunk not to sag. So that will allow it to go up and down. And 2 helical muscle. And so we really wanted to reduce the design to a much simpler 3-activator model. And based on the elephant, we have a design where we have 1 big longitudinal one and 1 left and right helical fibers. And now you have 3 activators, and you want to know what is the possible shape. And because we can do that very efficiently within this one-dimensional reduction theory, which typically soft robotic cannot do, you can sample millions of trajectories, and these are what's called the reachability cloud, which are all the points that if I touch my elephant trunk here and the tip is here, these are all the points that I can reach in space. And I can show that it's a much better design than having other type of design. We've looked at different type of optimization for that. And the last thing you can do, now you can actually realize that with strips of a liquid crystal elastomer that you can activate, and you can show that depending whether or not you activate one or the blue one or the red one or multiple together, now you can both control curvature and torsion. And we have a paper with René Zhao, who's done all these nice experiments in Stanford that explain all these. That's being peer reviewed right now. So I'm almost running out of time. Just want to conclude briefly. I wanted to give you a lot of different general idea about the problem I've been thinking about chirality of handedness. You see, it's a problem that comes in everywhere in natural philosophy. It's plant, seashell, and physics. It's related to, it has different names: handedness, chirality, parity, symmetry, and isotropy. The story of it is very confused, and you see that even mathematicians have really struggled with a proper definition, mostly due to the fact that they refuse for the longest time to refer in a mathematical text to any part of the outside world. And in this case, it's impossible to define left and right without doing so. That you can build chirality measure being inspired by aspect of physics that really are geometric objects that characterize better the geometry of this structure. That soft chirality is surprisingly counterintuitive. I told you about the helix. If you do the same thing with the tube, the results are completely different. If I take an elastic tube with fiber reinforced structure, helical fibers, I would have yet a different type of response. So there is also a lot of confusion. And the main point is that the chirality that you observe in nature is not only due to geometry, it's also due to material symmetry and mechanical force. So the internal geometry of the system. If I take a tube, one of these tubes that you show in the picture, if it's helically reinforced and I don't know it, if I pull on it, it will rotate. There is nothing in the apparent geometry of the tube that would tell me why it should rotate more left or right. So there are other fields inside that are important to consider. And that's why I call that soft chirality. In terms of transfer of chirality, there are multiple sources of chirality that you can identify, geometry being one, material symmetry being others ones, residual stress being otherwise. And there are a lot of very delightful examples of that in terms of instability. The tendril that I show you is an example of curvature-driven instability that create left and right structure. The problem in the seashell, we've looked at the difference between cephalopod and gastropod, and you can show that the chirality is induced by compression. And the problem of phycomyces, which is yet another problem, is a problem driven by twist. And I'm going to conclude there. Thank you.
Thank you very much, Alain. Wonderful talk, and it's a fantastic journey that we went through with you. I am very, very much impressed by a number of very important concepts and history that you outlined. I wonder, questions from the audience live?
Yes, I have one. Thanks so much for that fantastic talk. And I'm just curious, have you looked into zDNA, the left-handed version, at all during your investigations?
Uh, yeah, so and it does. It just has different energy landscape. But the only thing I want to say is that the difference, of course, BDNA has a very different geometry that you can see. I never look at the experiment where you can do transition between or melting transition between one to the other one. But I've never looked. I'm not. I have to say I'm not a DNA expert. There are people who know this type of of system much better than I do.
Okay. Yeah, thank you. I was just curious. Appreciate it.
Other questions, please.
Yes, Ellen, I do with something to say. I've got a chirality story for you. So this is
good.
about 1987. I was visiting in Zurich, and my friend Andrei Stasiak arranged for me to talk to Vladimir Prelog, the guy that got the Nobel Prize for chirality of molecules. So Prelog told me, he said he'd been reading Reidemeister's book on knot theory. And that, he got through alternating knots, no problem. He got to non-alternating ones. To hell with it, he quit. But he was telling me that the way topologists do it is you take a projection of an oriented knot, and the right-hand rule tells you whether crossing is plus or minus. He said that convention was wrong. Not that it was different from his, it was wrong because it didn't agree with his convention. So I said, okay, sounds good to me.
Yeah, so Tate and Maxwell had his argument because Tate used the other convention, of course, which is the quaternion. And so they always had this argument about left and right.
Yeah.
Well, by the way, Alan, you didn't mention orientation or the role of orientation. That makes also things a bit more complicated in classifying chirality and all that.
Sorry, what do you mean by that, by orientation?
Well, for example, you consider a trefoil knot, and then according to the orientation, you can classify further the invertibility of the knot
Sure.
with respect to the mirror image, etc. That adds kind of sophistication to the. But I saw Keith ready for a question. Keith, sorry, go ahead.
Oh, hi, Renshaw. Thank you. I thought it was a beautiful lecture, Alain. Lovely, full of very interesting points. Wonderful. But if I go back to your Q tensor, symmetric tensor, is that you were focusing on geometry at that point? Is it a topological invariant as well?
No. I mean, its trace being 0 is the only topological invariant. I don't think it's a topological invariant because it's very much dependent on the shape.
Yeah, that's what made me wonder, because I mean, in fluid mechanics, we tend to be very familiar with the other measure of chirality, that is helicity, which for a torus knot, for example, would, I think, work out at something like +3 if you have unit flux along the +3 if you're in a right-handed system of coordinates, -3, it changes sign, of course. It's a pseudo-scalar, but it is a topological invariant. In other words, if I deform that knot in any way you like without any crossing, it is invariant. Do you have some kind of idea of a link between your geometrical measure and that sort of measure?
No, I've looked at trying to. So there've been attempts to not by me, to look at how chirality or helicity tensor of certain type are related to one that you can attach to. In your case, you attach it to a vector field, which is different than attaching to a given geometric structure. And there was that I never could find good connection between the two, really. These are really chiral properties, that more than topological. These are geometric properties. That's what I wanted to emphasize.
Mm.
I have a curiosity, Alain. I'm sorry, I will formulate my question in a very, very, how to say, unsatisfactory way, but I try anyway. You, at a certain point, you showed in many instances, several slides, the case of perversion. And when you show the, say, the helical, there were sketches where the straight helix had a perverted state at the center, and then you pulled under tension this structure. I wonder, I'm just curious to, learning from your talk to be, any intuition might be wrong. I wonder energetically, the state of perversion in a structure is more expensive than having none at all of it, because okay, it makes sense. Because if I interpret, go ahead. Sorry.
So definitely, so if you have a straight structure and it has pure intrinsic curvature, and you put it under tension, the two global minima are either a left-handed or right-handed structure. But because you constrain them and you prevent the rotation in the end, it cannot attain that. It's forbidden to reach that state. So it has the next best compromise in energy is to have a left-handed and right-handed and pay that little price with a jump in between the two.
It's very interesting because, as Keith Moffat surely remembers, the work we did together and during my PhD under him was to encounter the problem of inflectional state. And inflection is just when you go from one concavity to the other, and so you go through an inflection that, of course, for a curve can be just one point of inflection, if you like. But there is a kind of similar situation there where you invert the curvature, say, sense of your helix into another one. So you have to go through a configuration that, in a sense, can be considered inflectional.
Yeah, but there is never a singularity because you do that in 3D. So you avoid any singularity. The curve is completely regular for this inversion.
No, I understand that, but that's interesting. The fact that you pointed out that energy is probably higher in the presence of these states. So that's quite interesting.
Yeah, you can play the kind of game that you can do in physics where you quench rapidly the states and then you have a lot of different inversion. It's a higher energy, but you reach these states dynamically. These are and it's very easy to do the experiment. If you take a telephone cable and just unwrap it and you take it long enough and pull on it and then rapidly release the tension, you'll find a lot of inversion like that.
So that means that if I think of a particle orbiting, forming whatever loop may form in space and not, when it has to invert somehow its sense of rotation, that is probably a case where energy is higher. Anyway, interesting. Other questions, please. All right. If not, well, thank you so much, Alain. Thank you very much, and have great holidays in the coming week. All the best.
Everybody have all a great holiday. Very nice to see you, Keith and Renzo and DeWitt.
Yes.
Thank you very much. Great talk.
Happy Christmas, Alain.